ladies and gentlemen. Welcome to the mini course on computer simulation of macroeconomic models that are given by Professor Karsten Kohler from the University of Leeds. Let me see a brief of his CV. Ideas on page of his.
Márcia?
Well, Professor Karsten Kohler is associate professor in economics at Leeds University Business School. His research crosses disciplinary boundaries and draws on macroeconomics, finance, and political economy. His interest in the interaction between finance and the real economy, especially sources of cyclical dynamics, instability, and rising inequality. He had published research on the distribution effect of energy price-driven inflation, the role of gross capital flows in financial instability, the interaction of business and financial cycles, the role of flexible exchange rates in emerging market business cycles, the effects of financialization on income distribution, as well as the role of house price cycles in national growth models across countries. His work has been published in journals such as the Cambridge Journal of Economics, the Energy Economics, the Journal of International Money and Finance, Oxford Bulletin of Economics and Statistics, Review of International Political Economy, Structural Change, and Economic Dynamics. He is also a member of the Post-Keynesian Economic Society, in which he is in charge of the working papers of the association. And he has recently co-led the work package on the drivers of currency tail risk in low and middle income countries for the research project Enhancing MDB Capacity Through Local Currency Lending, funded by the MDB Challenge Fund. Previously, he co-led a work package on financial instability and growth models for the project The Political Economy of Growth Models in the Age of Stagnation, funded by the Leverhulme Trust Grant. He also created, and is basically the objective of this course, the DEI Macroeconomic Model Simulation website, which provides free resources to simulate macroeconomic models in the programming language R and Python. So, Karsten, the floor is yours, please.
Yeah, good afternoon, everyone. Thanks, José Luis, for the kind introduction and kind invitation to run this session. I'm also amazed that so many people have signed up for this and joined the session, so that's great. Before we start, just some housekeeping issues. So this is meant to be an interactive session. So I will talk a little bit and then I'll give you some codes and the ideas and a little exercise, and the idea is that you try to run those codes on your own machines, solve some little problems, and then we'll go through the solution together, and then I'll talk a bit more, introduce some more content, and then there will be another lab exercise and another little exercise. And so the idea is to keep you busy and get you involved. And for that, it's important that you have access to the slides. So I put the slides in the chat. Please download the slides. The slides are in HTML format, so you can open them with any browser you like, Chrome, Firefox, whatever you're using. And then you can walk through the slides on your own machine as I go through the session. And the other thing that you would need is access to R and R Studio. Or actually, you don't necessarily need R Studio if you don't want to use R Studio, but you definitely need access to R to take part in the lab session. So yeah, my my advice would be download the slides, open them in a browser, and then also open R, so that once we get to the lab session part, you can run some simulations yourself. And the other thing is that, of course, I'm always happy to answer questions. So if there's anything that you don't understand, you don't follow, or you want to ask, feel free to just raise your question directly. You can also use the chat, but I can't promise that I'll be able to keep an eye on the chat. So I think the best way to make yourself heard is just by talking to me, and then I can answer your question. But you can also use the chat, but I might only get to looking into the chat when we're taking a break or something like that. Slides are not available in the chat, so let me just upload them again. Okay, is it working now? Okay, perfect. All right, then let me share my screen. Okay, so I'm sharing the. I'm not sharing the right window, I think. Sorry, I don't use Zoom that often. I mostly use Teams. So try this again. Okay, can you see the slides now? I mean, the ones that I'm
Yes,
sharing.
I'm seeing introducing the DIE.
Yes, perfect.
Okay.
Perfect. Thanks. Yeah, that's what I want. I mean, these are essentially the same slides that I just shared with you. Yeah. So you can either look at the Zoom window, or you just walk through the slides on your own machine, whatever you prefer. Okay. Yeah. Then so let's get started. So the plan for this session is, like I said, there's a couple of lectures that I call lectures, where I introduce the content, a bit of an overview into economic modeling in general, and then I want to talk a bit about simulating economic models. And then there's a lab session where we'll go through an example, and there will be some code for you to run, and you have to modify the code a little bit as a little exercise to see how it works. And then I'll talk a bit more about dynamic models, and then we have another lab session where we simulate a dynamic model. And then in the last part, I want to introduce directed graphs and show you how you can create directed graphs in R. So that's the plan. I think we have 3 hours, so I suggest we take a break in the middle, and then we see how far we get. I don't know if we're going to be able to cover everything, but yeah, we'll see how far we get. Okay. Yeah, I want to start out by talking a little bit about economic modeling. What is economic modeling good for? How does it work? And then we can dive more specifically into numerical simulations of economic models. Yeah, what is economic modeling good for? Why are we doing this in the first place? What are the benefits? In my view, I think the main purpose of economic models is that they help us to theorize causal mechanisms. So they help us to think through causal mechanisms that are typically interlinked, so that involve multiple variables and multiple causal relationships. And they offer a highly precise and formal representation of these causal mechanisms. And this is useful for analyzing these causal mechanisms in a very rigorous way, to be logically consistent in your analysis of a theoretical causal mechanism you're interested in. That's the main benefit of economic models. And this is especially useful when the variables that we're dealing with are inherently quantitative. So in particular, in macroeconomics, we deal with quantities such as interest rates, unemployment, inflation. So these are all variables that are inherently quantitative. You can measure them in quantitative units, and they are being measured by statistical offices, and we have access to these data. So the variables we're talking about in macroeconomics that are inherently quantitative. It's not too complicated to come up with a quantitative way of measuring those variables. And this is one of the reasons why I think macroeconomics is particularly amenable to mathematical modeling. And secondly, when we have multiple variables that interact with each other, we tend to have more complex causal mechanisms. And this is another reason where, or another configuration, if you like, in which macroeconomic modeling becomes useful, because once you're dealing with multiple interlinked variables, it can be quite hard to keep track of how all these variables are impacting each other and what the final outcome is of some kind of causal intervention. And this is where economic modeling becomes really helpful, because the use of equations and analyzing these equations as a system in which all these variables are connected is really the safest way of making sure that your analysis is coherent and consistent and takes account of all these interlinked mechanisms. So just to give you an example for this, so say we're interested in the effect of government spending on unemployment and inflation, classical macroeconomic research question. We might have some reasons to believe that there's a causal mechanism that links these variables to each other, where government spending may have some impact on GDP. GDP in turn may have some impact on unemployment. Unemployment then in turn has some impact on inflation. Inflation may have some impact on income distribution. Changes in income distribution can then have feedback effect on GDP. So you can see that for a typical macroeconomic research question like this, we're dealing with a fairly complicated causal mechanism that involves several variables and then also feedback effects between these variables. And models really help us to analyze this interplay of these interlinked causal mechanisms. And this then can be useful to work out the total causal effect, for example, of a policy intervention like an increase in government spending after this full causal mechanism has played out. What's the final effect on unemployment and inflation after all these causal effects between these macroeconomic variables have played out? Okay, so that's one of the main reasons why macroeconomic modeling is useful, or economic modeling is useful. Now, the next question is, how do we do it? So the key ingredients to pretty much any economic models can be grouped into three categories. So we typically have a set of equations, and we can count the number of equations. So we typically have n equations that specify the determination of a set of n endogenous variables, what we call endogenous variables, the variables that are determined within the model. And we want the number of equations to be equal to the number of endogenous variables for the model to have a unique solution. And then the third ingredient is a set of fixed coefficients, or sometimes called parameters, and exogenous variables. So these variables and parameters, they don't change within the model. They stay at the same value, and that separates them from the endogenous variables that are determined within the model. The equations that make up the model, they essentially specify causal relationships. So we're saying, for example, that the variable y is determined by a variable x. And the equations that we put into the model, they make explicit these hypothetical causal relationships. The solution to a model then tells us how the endogenous variables of the model, that you can think of the outcomes, react to changes in the exogenous variables of the model, which you can think of the causes. And this is then useful, for example, for explaining major macroeconomic events. So let's say you're interested in the relatively recent inflation episode that many countries went through between 2021 and 23. So then your outcome that you want to explain is inflation. And you might have some causes that you believe have driven this outcome. For example, changes in global energy prices. And you could then use a model to study how a change in an energy price would impact an outcome such as inflation, and could then generate a historical macroeconomic event such as the 2021 to 23 inflation episode. But beyond explaining macroeconomic events, we can also use models for policy analysis. So once we have a model that we find plausible, we could use that model to work out the hypothetical effect of an increase in government spending on unemployment, inflation, and so on. So this is an example I gave before. This can then inform macroeconomic policy, for example. And lastly, models can also be useful for conducting econometric analyses. For those of you who have done some econometrics, you know that for the parameters that we want to estimate in econometrics to be unbiased, the explanatory variables of the regression equation that we want to estimate, they need to be exogenous. And having a model at hand can help you think about this question of how you can identify exogenous variables and what are the potential sources of bias in a regression equation, such as simultaneity or omitted variable bias. With a theoretical model at hand, you can think about these questions much more systematically, and this can then inform your econometric approach as well. So like I said, to be able to make a statement about what the total causal effects of an intervention is according to a model, the model needs to be solved. And the model can be solved in different ways. And I think many of you will have encountered this sort of traditional mathematical way of solving a model, which is the method of substitution. So if you have a small model with only a handful of equations, you can substitute the endogenous variables into each other, and in this way work out the solution to the model with pen and paper by hand. That's how many of us have solved economic models in our studies. If you have a linear model, you can also cast the model in matrix form, such that you have a coefficient matrix A that collects all the coefficients that are multiplied, or the parameters that are multiplied onto the endogenous variables x. So the endogenous variables are collected in the vector x, and then you have another vector b that collects all the intercepts, and you can then find the solution to the model, the solution for the endogenous variables, by taking the inverse of that coefficient matrix A. So that's the linear algebra approach in a way to solving a system of equations if you have a linear system. And some of you may have also done that in your studies. So that's the mathematical approach. And an alternative approach is numerical simulation. So numerical simulation provides an alternative way to solving and analyzing economic models. And this can be done with open source programming languages such as R and Python. And the main advantages to this numerical approach that I want to introduce in this session is that it is easy to do. So basically, you're sidestepping the algebra. You no longer need to sit down and do the maths and move around terms in an equation and make sure you don't make any errors. So you get rid of all the tedious algebra. And that is a major advantage, if you like. So in that sense, it's relatively easy to do. It also has certain intuitive appeal, which might become clearer once we run a simulation ourselves. I do think that simulation can help building intuition for an economic model, but I think that's best. You will see that yourself, I think, once you start playing around with that a little bit yourself. Then another advantage is that we can use numerical simulations to confirm an analytical solution. So that's very helpful when you're working with your own model. So let's say you're working on a small scale model that has some analytical solution, and you worked out that analytical solution algebraically. But you might not be sure that your solution is correct. You can then simulate the model and use the simulation to confirm your analytical solution. So that can be very helpful to have that certainty that your calculations are correct. But then, of course, we can also use numerical simulations to solve more complex models, and in particular, nonlinear models that may not have an analytical solution, or the analytical solution is basically impossible to find. And that this is where the numerical simulation becomes really useful. Jose, do you have a question?
No, just a small remark. The remark is that models that have mathematical solution do not necessarily have an economic solution. Just to make this simple observation.
Yeah, that's true, of course. And I think this is also something that you might discover as you study a particular model by means of numerical simulation. It can really help you to understand the mathematical properties of a certain model, and then also ask the question, to what extent are these mathematical properties economically meaningful, and are there some mathematical properties of a model that perhaps we want to rule out because they're not economically meaningful. So in a way, the numerical simulation can really help you explore a model and better understand what it does and to what extent it has economically meaningful properties or not. Yeah, and finally, one way of doing that is through visualizing the results of a model, where numerical simulations also provide some ways of visualizing models that you might not find in the more traditional textbook approach, where we have the well-known curves that we are shifting around to understand properties of economic models. The numerical simulation give you different ways of visualizing models, and that can also help build intuition. Okay, so this brings me to the DIY macro simulation website, and I want to just say a few words about what that website offers. So maybe the best way of doing it is just quickly open that website, and I'll just show you very briefly the main structure, and then of course best way to explore the website is to take some time, take a look at it at home. But just in terms of the broad structure, so what the website offers is, if you click on the first chapter, the Getting Started chapter. There you can get some information about how to access R and Python, and some online resources for learning the basics of R and Python. And then we also provide on the website a little introduction to R and Python with some information about elementary operations, things like if-else statements and loops. And then there's some little exercises here that you can work through, and we provide the solutions here as well for you to check. And we have codes for both R and Python. So the default setting is that we'll give you the R code on the website, but if you're interested in the Python code, you just click here, and then the corresponding Python code will become uncollapsed, and then you can access that Python code if you're interested in Python. So that's the first chapter of the website. It gives you a brief introduction to these two major programming languages. And then there's a chapter on how to simulate economic models. So that's what I want to talk about today in this session. But you can also later on, if you want to, if there's something you didn't understand or whatever, you can just read through that chapter on the website. And then after that, we have a series of economic models. Just applications, really. And these are grouped into two categories. So we have static models and dynamic models. And today in this session, I'm going to introduce one static model and one dynamic model, so one from each group. And maybe just to pick a random example, the ISLM model. So every entry, every chapter on a model starts with a brief overview of the model. What is the model about? What are the origins of the model? And then it just presents the model, the equations of the model in a concise way. So these are the equations of the ISLM model. And then there's some brief explanation of the economic meaning behind those equations. And then you have a section on simulation. So we present the parameter values that we use in the simulation. And for every model, we consider different scenarios. So we have a baseline scenario. And then here in the case of the ISLM model, for example, scenario 6 is a fiscal expansion, for example. So we look at a change in exogenous government spending and then how that impacts the endogenous values of the model. And we have a couple of other scenarios here as well. And then we give you the simulation code. And I'm going to go through an example of this in a minute. And some plots that give you the results. And there's a bit of a discussion in the text as well about, what are the key takeaways from this model. And then we also have for every model a directed graph. So later in this session, I'm going to explain a little bit what a directed graph is, but it's a way of representing the causal relationships in the model through nodes and arrows. And there's code here as well that generates that directed graph. And then the last component for each entry is an analytical discussion where we go into the mathematics of the model. So we have, in a way, we supplement this numerical simulation with the more traditional mathematical way of solving the model. And we also, here in the end, for example, we show the correspondence between the numerical results and the analytical results. So, for example, we can calculate the fiscal multiplier in the ISLM model either numerically, or we can use the analytical solution for the fiscal multiplier, and it should give us the same result. Just to sort of illustrate that if your maths is correct, or corresponding if your simulations are correct, they should give you the same answer. And for a simple model like the ISLM model, we can show this very easily. Yeah, so just for you to have an idea of how a representative entry on this website looks like. And you can see we have a bunch of different models here, from some classic textbook models like the ISLM model, some models here from the post-Keynesian tradition, Calder-Robinson model, post-Kaleckian model. We also have a new Keynesian three-equation model. We have some models from the history of economic thought, a Malthusian model, a Ricardian model. So there's a variety of different models. And we also keep working on this website. So I think every year we're adding 1 or 2 new models to the website. Depends a bit on how much time we have. But yeah, it's a website that is growing over time. Maybe just one more thing to mention, which is this chapter here, chapter 9. That gives you an introduction into the mathematical analysis of dynamic models. So today we won't have time really to go into this. But after this session, if you want to dig a little bit deeper into the mathematical analysis of dynamic models, I would recommend working through this chapter, because this gives you, in a way, the mathematical knowledge to analyze dynamic models mathematically. And this is, I think, very useful as a to complement the numerical simulation, so that you really understand how these models work. Okay, so that's the website. So let me go back to my slides. Okay, so that's the website. And what I want to do now in this session is, like I said, I want to introduce you to the idea behind numerical simulations, how they work. And then we will go through 2 examples. So we will first go through a static model, and then we will go through a dynamic model. And then in the last part, depending on how much time we have left, I want to show you how to create a directed graph of a model. Okay, let me see if there's any questions up to this point. Okay, I don't think there's any questions in the chat. Any questions? Okay, if not, then let me talk about these numerical simulations. How do they work? I want to start with a very simple example, which is a simple Keynesian aggregate goods market model. Yeah, so we have a model here with 2 equations and 2 endogenous variables. The 2 equations are an aggregate output equation. So aggregate output is given by aggregate demand, and aggregate demand only consists of consumption and investment spending. And we have a consumption function. So that's the second equation of this model, where we assume that consumption is given by an autonomous component C0, and then a marginal propensity to consume out of income. Yeah, so C1 is the marginal propensity to consume out of income. So these are the 2 equations for 2 endogenous variables, Y and C. Now, we can use the conventional method of substitution to find a solution to this simple system, which I'm pretty sure all of you have seen before. That's famous Keynesian goods market model. And yeah, we can find this solution here by substituting the equation for output into the consumption function, and then substituting that back into the equation for output. Yeah, so I'm sure you've seen that before. Now the question is, how can we find a solution to a simple model like this through numerical simulation? So the approach that we are using on the website is based on iteration. So the way it works is you firstly choose a set of numerical parameter values. So in this Keynesian model, the two main parameters are the parameters of the consumption function. So the autonomous consumption demand C0 and the marginal consumer income C1. So we need to choose numerical values for these fixed parameters. So for example, we choose a marginal consume of 0.8. And then the next thing we do is we choose arbitrary but non-zero initial values for the endogenous variables. So the endogenous variables, like I said, in this model are consumption and investment. And consumption and output, so C and Y. And we need to assign an initial value to these endogenous variables. And the most straightforward way of initializing them is to initialize them at some arbitrary but positive value. So we can set consumption equal to 1, for example. And we then solve the system of equations many times using a for loop. And I'll show you in a minute how that looks like. But basically, we're using a very elementary coding tool that executes a set of code many times. And as these equations are calculated many times, the initial values we start from, they get overwritten in each iteration. And in the iteration, you always take the value from the previous period and you override it. And by doing this many times, you obtain the solution progressively. So you approximate the solution progressively. And by just making sure that you run this iteration often enough, so to speak, you make sure that the approximation that you get is satisfactory. It's close enough such that you would consider the approximation the correct solution to that system. So this is the basic idea behind the numerical simulation via iteration. And I'll show you how this works now. But the only thing I want to say before we go into the example is the main limitation that has to be borne in mind when simulating economic models is that we're always analyzing a special case. We can only solve the model numerically by picking certain numerical parameter values. Otherwise, it's not going to work. You need to decide, okay, I want to set the marginal propensity to consume, for example, to 0.8. And then you can solve the model for that, we call it parameterization. And you get a solution, but that's the solution of the model for a marginal propensity to consume of 0.8. So that means you're always analyzing a special case. You don't get a general solution to the model. You get a solution to the model for a particular parameterization. So that needs to be borne in mind, because the model might display different properties as you consider different parameter values. And the only way to find that out is by simulating the model for different parameterization. But especially models with more than 3-4 equations, they tend to have 3, 4, 5, 6, 7 parameters. The number of parameters increases quickly. And for every parameter that you add, you increase the number of potential parameterizations that you could analyze more than proportionally. So you get, in a way, an exponential increase in and potential parameterizations that are possible for every parameter that you add. So you very quickly have a very large number of potential parameterizations that are conceivable. And you really need to bear in mind that with a numerical simulation, you can only look at one parameterization at a time. Yeah, so that's a key limitation compared to the mathematical analysis of a model, which is much more general because it gives you a general solution to the model. Okay, but with that said, I want to show you now how this works. So this is the R code that simulates this little Keynesian goods market model into equations. So the first thing we're doing here is we're clearing the environment, which when you start out might not seem particularly relevant, because if you open R and maybe you open RStudio, you open an empty script, there's nothing there. But as you start generating objects, you might at some point want to delete everything and start from scratch again. So that's what this first line of code is doing here. This line here deletes all the objects from the environment so you can start from scratch. Now this is when it gets a bit more interesting. So the next thing we're doing is we set the number of parameterizations that we want to consider. Yeah, so in the following, we usually want to run a model not just once, but several times. And each time we want to consider a different parameterization for the model. So here we decide in advance on the number of parameterizations that we want to consider. And in this example that I'm showing you now, I want to set the number of parameterizations equal to 2. So I want to consider 2 scenarios. So that's why I'm setting S equals 2 here. Then in the next step, I'm setting the fixed parameter values. Yeah, so for the autonomous consumption C0, we set a value of 3. And for the marginal propensity to consume our income, we set a value of 0.8. Yeah, this is completely arbitrary at this point. Yeah, we just need to start somewhere. So we are setting fixed parameter values for these coefficients of the consumption function, and we can, if we want to, later run the model again for different parameter values. But this is what we're doing here for now. And then the next step is to create vectors in which the equilibrium solutions for the endogenous variables from the different parameterizations will be stored. So in our case, we have 2 endogenous variables, output and consumption. And we want to create vectors which are objects in R that allow us to store data. And these, in the first instance, we just create 2 empty vectors that later will contain the equilibrium solutions for output and consumption. So here we're creating these empty vectors. Yeah, we call them y-ec and c-ec, yeah, for the equilibrium solutions. And we say that we want the vector to have length s, and s is the number of parameterizations that we set before. Yeah, so we're creating a vector that will have 2 elements here, and that vector will contain the solutions for output for the first and then for the second parameterization. Now, the next thing we do is we create vectors that will contain the exogenous parameters or exogenous variables of this model that we want to change across parameterizations to see how that impacts the endogenous variables of the model. In our case, the exogenous variable or parameter that we want to vary across parameterizations is investment. Yeah, investment is exogenous in this model. And we want to consider 2 different parameterizations for this model. The one in which investment is set at a value of 5. And then in the second parameterization, investment goes up to to the value 6. Yeah, and in this way, we can assess what happens to the endogenous variables of the model as investment goes up from 5 to 6. And here you can see what I'm doing is I first create this vector I0, that's the vector for investment spending. And then I use this notation here to access the first element of the vector and assign the number 5. Yeah, so with this line of code, I say, okay, take the investment vector and assign the value of 5 to the first element in that vector. And in this line of code, I do the same thing for the second element of the vector. Yeah, so these squared brackets, they allow us to access the elements in a vector or a matrix in R. Yeah, so that's what we're doing here. Maybe just to illustrate this, how this looks like. I'm just going to run this quickly on my computer to show you. Can you see my R Studio now, or do you still see the slides?
I think that the slides yet.
Okay, yeah, then let me change this so that I share my screen instead. Okay.
Now, yes.
Yeah, I just want to show you quickly how this looks like. So let me run these first 20 lines of code here. Just to show you how these, so you run this, if you use RStudio, the objects that you created, they appear here in this window on the right-hand side. Yeah. And so we created the vector for consumption, output, and for investment. If you want to see how this vector for investment looks like, you can go down to the console here, and you can just type I0 and hit enter. And then it will print the content of that vector. And now you can see we have a vector here that contains the numbers 5 and 6. Yeah, so that's what we wanted. These will be the values for investment across the two parameterizations. You can also print the vector for output. And you can see this at this point, it just says false, false, because it's empty. Yeah? It doesn't contain anything at this point. And in the simulation, we will then fill that vector with the data. Yeah, but at this point, we just create this empty vector. Okay, then the next thing we do is we initialize the endogenous variables at an arbitrary positive value. So we just use a value of 1 for our output and consumption. So we run that. That creates variables for output and consumption that have the value 1. And now this is where the heart of the simulation is in this these couple of lines of code here. So what we're doing, so what we're having here is it's called a nested loop. In a way, we have two loops that are nested into each other. So it looks a bit complicated at first sight. I want to break it down by focusing on this inner loop here first. As this is really the loop where the system of equations is solved. The way a for loop works is that it executes the lines of code that are inside the loop many, many times. Basically, as often as you tell R to run these lines of code. So if you look here, what I've highlighted, we have these curly brackets. The first curly bracket opens the loop, and the last curly bracket closes the loop. And the two lines of code that are inside the curly brackets, these are the two lines of code that are being iterated while the for loop is running many times. You can see that the two lines are the two equations of this Keynesian model. Yeah, so we have the first equation, the aggregate demand equation, and the second equation is our consumption function. So these are the two lines that are being iterated many times while this for loop is running. Now let's take a look at this part. So here, what we're doing is we're saying by typing for, R knows, okay, you want to construct a for loop. So you type for, and then you need to specify inside the regular brackets how exactly you want this for loop to work. Now here, by putting the 1 to 1,000, we are telling R we want this loop to run 1,000 times. Meaning we want to run the two lines of code that are inside the loop. We want to run those lines 1,000 times. Yeah. This word iteration here actually doesn't have any function. It doesn't do anything relevant. I just put it there to emphasize that this is an iterations loop. The only thing it does is it iterates these two lines of code inside the loop 1,000 times. I will explain to you in a minute what the potential purpose is of this part that is inside the regular brackets. For this iterations loop, the only purpose is to specify the number of iterations you want to run. Okay, that's the loop that solves the system of equations. Now I said this is a nested loop, so it's actually embedded in a second loop, and this is this loop here. This is the outer loop. This outer loop starts with that curly bracket there, and it ends here in line 35. What does this outer loop do? The outer loop loops through the different parameterizations that we've constructed before. Yeah, so we constructed two parameterizations, one where investment is equal to 5 and a second one where investment is equal to 6. What this outer loop does is it solves the model once for a value of investment of 5, and then it solves the model again for a value of investment equal to 6. And then it saves the results from these two different parameterizations inside these vectors that we created in advance. Yeah. So you can see that here, when I create this loop that goes through the scenarios, what I wrote is inside the regular bracket, I wrote I in 1 to S. So the 1 to S says, run the lines of code that are inside the loop S times, and S in our case is just 2 because there's only 2 parameterizations in this example. And now this letter I, the lowercase I here, this has a purpose now. Yeah, this plays a role. What this I letter does is it assumes the value 1 in the first iteration of the loop, and then in the second iteration of the loop, it assumes the value 2. And you can see that the letter I appears here in the output equation when we call the vector that contains the values for investment. Yeah, so this I0 was our vector that contains the data for investment. And you can see that we're indexing this vector with the index number I. And the index number will select the relevant element from the vector. Yeah, and this is this index number will change as we loop, as we go through the loop from 1 to 2. Yeah, so in the first iteration of this outer loop, the index number I, or index letter I, will assume the value 1, and so we will pick the first element from the investment vector, and we solve the model for a value of investment of 5. Once that's done, we will run the whole thing again, and this time the index letter I will take on the value 2. So we will pick the second element from the investment vector, and in this way we solve the model again, but this time for a value of investment of 6. Yeah, the second element from that vector. And then these two lines of code, what they do is they take the last value from the iteration and stores them into the solution vector that we previously constructed. Yeah, because these variables y and c, they are they only assume one number. Yeah, so they are scalars, as we would call them in linear algebra. They just have one value. In every iteration, the value is overwritten. Yep. So as we run these inner loop 1,000 times, the value for y will be overwritten in every run. And then after 1,000 times, we have a final value for output, and we take that to be the solution. And we store that value in this vector that we created before, and we treat that as our equilibrium solution for output for the parameterization I. Yeah, so this is what happens here in these two lines, and then we close the parameterizations loop, and then we're done. Yeah, so then we have our results. So let me run it and show you what it does. So it's super quick. You see, it has already run these lines of code 1,000 times, twice 1,000 times. And here I just display the solution for output, and they're being printed here at the bottom. Yeah, and so you can see the solution for output for the first parameterization is 40. And the solution for the second parameterization, where investment goes up from 5 to 6, then the solution for output becomes 45. Yeah, so these are our solutions. Okay, so I can see there's a question in the chat. How do you choose the number of parameters of the model? Arthur, I presume you mean the values for the parameters, right? Because, I mean, the number of parameters is given by the model itself, right? But I presume what you mean is the parameter values here. Yeah, so this is related to the point I was making earlier, that in a numerical simulation, you can only look at one particular case at any moment in time. Yeah, so you always solve the model for a particular parameterization, and that's the main limitation of the numerical simulation. So in a more complex model, I don't know. You have to start somewhere, yeah. So I guess in practice, the way you do it is maybe you set the parameters at values that are considered realistic. Sometimes we have parameters such as the profit share, for example, where you know, we have some data, so we can set profit shares at realistic values for a particular economy that we want to analyze. But for behavioral parameters, such as the marginal propensity to consume, yeah, we don't know necessarily what a realistic value is, but you can start somewhere. You can look at estimates for these parameters in the literature, in the empirical literature. But yeah, basically you have to make a decision. And you can then explore the sensitivity of the model to changes in the parameter value. Yeah? So then that once you run them, you simulate the model successfully, you can simulate it again for a different parameterization, see how that changes the results. Yeah. And I mean, the good thing is that now with we have a lot of resources in a way to do numerical analysis. So you can run a model for many different parameterizations. And you know, so this is possible. But like I said before, you can work out with like combinatorics, you know, the number of potential parameterization. This is a huge number. Like for any medium-sized model, the number of potential parameterizations is going to be so large that you will not be able to consider all of them. Yeah. So in that sense, you will always only look at a snapshot of what's possible. There's a question from Claudio about advantages of parametric models over non-parametric models. I'm afraid I don't understand this question. Can you clarify what you mean by parametric versus non-parametric?
Hi, Karsten. You said that in page 10 that this model is basically a parametric model, and it can be only used in a specific range of parameters, okay? But nowadays, we know that it's possible to have solutions with non-parametric solutions, like machine learning and deep learning models. And what do you think is the great advantages of these parametric models over the non-parametric models?
I mean, I think at a very fundamental level, you can only solve the model by assuming a certain parameter value. I think that's I don't think there's any way of getting around that. So I think what you can use, what maybe machine learning tools offer, is you can explore the parameter space by using certain algorithms that where you I don't know, you might put in some real world data. You say, okay, I want to match certain statistical moments, for example. You know, you take some, I don't know, GDP inflation data, and you extract moments from those data for an economy, and then you have certain algorithms that would run your model, trying out different parameterizations, and then finding a parameterization that give you a close match to these empirical moments. So that's one way of calibrating your model. Yeah. So, for example, something that's not even using machine learning is method of simulated moments. That's, for instance, something that we've used in a paper on inflation that I've written with some co-authors, where we calibrated a model using a method of simulated moments, which takes empirical data and then explores the parameter space of your model, and then finds the parameter combination that makes your model's data match the empirical moment as best as possible. So yeah, there are techniques for doing that, for sure. Yeah. But yeah, we don't cover this on the website. Our website is much more introductory, so it's more about you know, learning how to run a simulation in the first place, learning how to how to analyze a model and see what a model does. And at this point, this is a completely theoretical exercise. We're not really trying to match any empirical economy. We're just trying to understand the model in the first place. So yeah, these techniques are a bit more like for more advanced research, I'd say.
Okay, thank you.
Yeah, but thanks for the question.
Karsten.
Yes.
There is a question from someone in YouTube. Hello, Mr. Kohler. Thank you for the presentation. As I understand it, the initial set of parameter values here are analogous to priors in Bayesian inference, but only for point estimates. Here's the question.
No, I think this is overthinking it a little bit. I think there's nothing Bayesian. There's nothing also like statistical at all going on here. I mean, there's no. We're not really bringing in any real world data here. Yeah? We're just finding a solution to a mathematical model for a certain randomly chosen set of parameter values. That's the only thing we're doing. Yeah? So there's nothing Bayesian frequentist or anything going on here. Yeah? It's just literally just solving a system of equations. That's the only thing we're doing. In terms of convergence, this is a good question, because it is true that this approach, this solving the model through iteration, will only converge in a way to the equilibrium solution if the model is stable. Yeah. We can maybe let me illustrate this with an example. So let me just quickly go back to the slides. Okay, so the solution we found for output for the two parameterization was 40 and 45. Yeah. So we can check that these solutions corresponds to the mathematical solution that we know for this very simple model. Yeah, by typing the mathematical solution. The mathematical solution for this model is autonomous consumption plus autonomous investment divided by 1 minus the marginal propensity to consume. Yeah. So if we run this, you get the mathematical solution to the model, and it is 40 and 45. So you can see that the numerical simulation coincides with the mathematical solution. So that's exactly what we want. Now, let's just to address this issue of stability. If we set the marginal propensity to consume, let's say to 1.2, yeah. If we set the marginal propensity to consume to 1.2, then we can take the mathematical solution to the model, and we can work out that for this marginal propensity to consume, the equilibrium solution would be minus 40 and minus 45. Not economically meaningful, but it is mathematically that would be the solution. If we run the simulation for these parameter values, you can see that, well, actually, the solutions here that we find are incredibly large. Yeah, we get like extremely large values here for output. we don't get the values of -40 and -45. So why is that? Well, the short answer is because for marginal propensity to consume or larger than 1, the so-called Keynesian stability condition is not satisfied. So this model is unstable. And if the model is unstable, the solution that you get here for the equilibrium from this iterations approach is not the equilibrium solution, because this equilibrium is an unstable equilibrium. And we initialize the model at a value of 1, which is not, we're not initializing the model on the equilibrium. And by iterating the model from this initial value, which is off equilibrium, and the fact that the equilibrium is not stable, we keep moving away from that equilibrium. And this is how we end up with these extremely large values for output, instead of the solution, which would have been -40, -45. Yeah. So in that sense, this for iterations approach, when it comes to finding the equilibrium solution, requires the model to be stable. Once we move to dynamic models, then in a way we make this question of the stability of the model more explicit, and we're asking that question explicitly, and then we can again use the simulations to maybe cast some light on this question of stability. But in this simple example where we just have a static model and we don't address the question of the stability of the equilibrium, it is definitely possible that we could pick a parameterization for the model, which happens to be unstable, and we run the simulation, and the only thing we get is these extreme values. Now, these extreme values will not be the solution to this unstable equilibrium, but at the same time, they're also not completely useless, because once you simulate a model like this and you get these insane numbers here, there's a clear sign here that the equilibrium is unstable. Yeah, so there's still some useful information to be gained from this, in the sense that this signals to you that you've simulated the model for parameterization where the equilibrium is unstable, and thus you don't converge to that equilibrium. Yeah. So just to address that question of instability. Okay, let me move on a little bit, and then we can take a break, and then we can discuss some more questions. But I just want to finish this part. Let me go back to the slides. Okay, so provided that we pick a value for the marginal propensity to consume that gives you a stable equilibrium, you can see here that the numerical simulation does coincide with the analytical solution. Yeah, so it does work for this simple example. So what I want to do is I want to give you a little exercise to run a simulation yourself. And then let me think about this. How much? Okay, maybe we do this and then we take a little break. Okay, we do this exercise, this first exercise, and then we take a break. Okay, so I want to show you how to solve a slightly more complex model numerically, but it's still a very simple model. But it has a few more equations than this Keynesian goods market model that I just showed you. The model that I want to simulate with you is a post-Kaleckian growth model. I don't know if you have encountered this model before or not. I will briefly go through the equation, but if you haven't never heard about this before, you might want to read up about this model later on, because I don't have that much time now to talk about the specifics of the model. So we just want to take this model as an example.
Karsten,
Yes.
Just to tell to everyone in the course that I have a book published in Portuguese that present the post-Galeskian growth model. It is called Macrodinâmica Pós-Keynesiana, Crescimento e Distribuição de Renda, published by Alta Books in 2018. So everyone that would want to know about the Galeskian or post-Galeskian growth models can buy my book, just my merchandising.
Yes, great, excellent, perfect. Yeah, the textbook that I used here is from Eckhart Hein. This is in English, but yeah, of course, amazing that to have that reference as well in Portuguese if you want to read up. It's a very standard model in post-Keynesian macroeconomics. So this model has 5 equations. We have the first equation here is an equation for the profit rate. So R is the profit rate, the total profits divided by the capital stock. And this profit rate is decomposed into the product of 3 variables. The first one is the profit share, for which we use the letter H. Then the rate of capacity utilization, so that's potential output. Sorry, I think this should actually be actual output over potential output. There's a typo here. So this should be the inverse. Output over potential output, that's the rate of capacity utilization. And then the last term is potential output over the capital stock. So the capital productivity, if you like. And so we can also write this product as the product of H times U, use the rate of capacity utilization, divided by V, and V is the capital to potential output ratio. So the inverse of the output capital ratio. Then we have a saving rate. So that's total savings divided by the capital stock. And in this model, we have saving out of wages and saving out of profits. So SW is the marginal propensity to save out of wages, and S pi is the marginal propensity to save out of profits. And if we allow both workers and capitalists to save out of their wage income and their profit income respectively, we can write this saving function like this. Yeah, so we there's some algebra behind this, yeah, that gives you this representation. But basically what this equation says is workers save out of wage income and capitalists save out of profit income. And then we have a consumption function, so which is just by definition giving by output minus or income minus saving, that gives you consumption. Yeah, so we take the rate of capacity utilization, we divide by the potential output ratio, so that gives you income. And from that, we deduct savings, and that's consumption just by definition. And then we have an investment function for investment over the capital stock, where we have an autonomous term, G0. Sometimes this is considered the animal spirits, the idiosyncratic investment decisions by firms. Then we have a rate of capacity utilization U, and we have the profit share H here in this investment function. So these are the main determinants of the investment. And then finally, we have the goods market equilibrium condition, which says that the rate of capacity utilization is determined by consumption and investment. And we need to multiply by V to make sure that the normalization that we're using here works out. So consumption plus investment multiplied by the capital potential output ratio gives you your equilibrium condition that aggregate output is equal to aggregate consumption plus investment. So that's the model. That's the post-Galeskian growth model. And now I want you to simulate this model. And I've given you the code here on the next slide. And what I want you to do is take the code. So if you in the slides here, if you hover here with the mouse in the top right, there's a little symbol here. If you click on it, it will copy the code, and then you can paste that code in your R script. And this code is already more or less complete. There's only two things that are missing, which is here you need to create the scenarios. And here at the very bottom, I want you to display the solutions. These are the only two things that you need to change. And I want you to construct these two scenarios for the profit share. Yeah? So a baseline scenario where the profit share is equal to 30%. And then a second scenario in which the profit share increases to 40%. Yeah, and then print the solution for the equilibrium rate of capacity utilization to assess what happens as the profit share goes up from 30% to 40%. Yeah. So let's take a few minutes for you to try this out, and then we'll take a look at the solution together. And if you have any questions, feel free to use the chat.
Karsten, Danielle is asking to send the slides again.
Yeah, I'll do that. I think it's probably when people join later, they don't have access to the things that were posted in the chat before. I don't know. Okay, I'll give you 1 or 2 more minutes and then I'll show you the answer. Okay, let's take a look. I'm gonna copy paste the code into my R script and share with you. Okay, so like I said, the only thing that's missing here is the parameterization for the profit share H. Yeah, so so we said, okay, we want to consider 2 scenarios. Yeah, so we set S equal to 2. And we want to set a profit share of 0.3 for the first scenario. So I type 0.3 here, and I need to assign that to the first element of that H that contains the value for the profit share. And then for the second scenario, I assign a value of 0.4. And I need to put in the number 2 here to index the second element of the vector. And then we can run the code. Everything else is already done, and it follows exactly the same logic as in this simple Keynesian goods market model that I showed you before. So we can run it. And then we want to display the solution. So I'm just going to type UEC, and I'm just going to run that. And these are the solutions that we get. So what do we observe here? What's happening here with the equilibrium rate of capacity utilization in response to this change in the profit share? What do we conclude?
It's falling.
It's falling, exactly. Yeah. So it looks like the equilibrium rate of capacity utilization is going down in response to this increase in the profit share. And for those of you who are familiar with these kind of models, so what is this kind of behavior? How do we call this? Does anyone know?
It was the wage-led, profit-led debate, right?
Exactly. And so what do you think? What do we have here? Is this a wage-led or a profit-led results? Yeah, okay. Someone in the chat wrote, Jackson wrote it's wage-led. Yeah, exactly. So it's correct. Yeah. So here we're looking at an increase in the profit share across these 2 scenarios. We find that the equilibrium rate of capacity utilization for the scenario where the profit share increases goes down. So in the literature, this is typically referred to as a wage-led demand regime, because aggregate demand, as measured, if you like, by the rate of capacity utilization, responds negatively to an increase in the profit share. This means that the demand regime is wage-led. And for those of you who are familiar with this model, you know that the model in principle can also give you a so-called profit-led demand regime, where the rate of capacity utilization would increase in response to an increase in the profit share. And so we would have to change the parameterization of the model and for certain parameterization, the model would become profit-led, and then you would get an increase in the rate of capacity utilization in response to this increase in the profit share. And I think this is maybe also useful to illustrate this problem or limitation of the numerical simulation. Yeah? So let's say you came up with this model from scratch, and you just simulated the model for this parameterization. You might now conclude, okay, I've created a model here in which economic activity is declining in the profit share, and that's a global property of my model. But this is not true. I mean, this model could give you a different result for a different parameterization when it comes to this question of the sensitivity of output with respect to the profit share. Yeah, and you would maybe only find that out if you would simulate the model many times for different parameterizations, and then you would realize, oh, actually, for different parameter values, I get a different regime. Yeah, so by contrast, if you do the maths, and I'm sure in Jose Luis' textbook, you will find mathematical solutions to these models that tell you exactly under which conditions this model generates profit-led or wage-led results. Yeah? So that's really, I think, important to bear in mind here that this is the key limitation vis-a-vis the proper mathematical analysis of a simple model like this. Okay, Jose, Luis, you want to come in?
Yes, I want to do just two remarks. The first one is that for this model to be stable, you have to make the so-called stability condition, which means that propensity to save must be higher than propensity to invest. Otherwise, the model will be unstable and can be a negative equilibrium value for the capacity utilization. Is my first remark. The second remark is that this kind of model, the post-Kaleckian or neo-Kaleckian model, are extremely sensitive to changes in the propensity to save. If you, instead of make this exercise of changing the profit share, you have changed the propensity to save, the result will be a disproportionate change in the equilibrium capacity utilization, which means that this model has the property which not seems to valid, that the sensitivity of the equilibrium capacity to change to small changes in propensity to save, the sensitivity is very high. So it's a problem that was detected by Peter Scott in a paper published in 2010, if I do not mistake, but it is a problem with this kind of model. Just these two remarks.
Yes, thanks, Jose. Yeah, definitely. So there's a debate around this post-Kaleckian model, and the model has certain properties that have been considered problematic or implausible or unrealistic. So that is, in that sense, the model here is really just an example of a canonical model at this point. But yeah, that model obviously comes with its own problems. I would say that, especially with respect to the second point you mentioned about the sensitivity of the model's results to the propensity to save, I mean, these are the kind of things that I think where numerical simulations can actually be helpful to notice properties like this, that by just playing around with the model, simulating it many times for different parameterizations, you get a feeling for what the model does and what its properties are. And this might make you aware of certain odd results that a model can generate. Of course, you can do the same thing mathematically, especially if a model is simple like this. But even with a relatively simple model like this, sometimes, in my experience, doing the numerical simulations does give you, in a way, like a different perspective on the model, or it suddenly makes you aware of a property of a model that you may not have noticed before, just by doing the mathematical analysis of the model. So I think that's where the numerical simulations can be very useful, to become aware of certain properties of a model that are not necessarily obvious right away from the mathematical solution. Okay, I suggest we take a little break now. I mean, if you want, there's a second exercise here about plotting this effect. So if you don't feel like you need a break, you can feel free to have a go at this second exercise. But I suggest we take 10 minutes break now, and then I come back to that second exercise after the break. So should we get back at 10 to 4, yeah?
Okay, perfect.
Okay,
Okay, people, see you later.
see you later. I can't find the chat. Okay.
Okay.
Welcome, everyone. Okay, so let's go into the second half of the session. Someone asked in the chat about Dynair, simulating DSG models in Dynair. The short answer is I have no idea. I've never worked with Dynair. I also don't work with DSG models, so I can't really make that comparison. The only thing I can say is that what I consider to be one of the main advantages of the approach that we are presenting on the website is that the way we simulate models is completely hard-coded from scratch. Yeah, we're just using base R here, vectors and matrices, for loops, that's it. And same thing in Python. The way we constructed the Python counterpart to the code is we use the NumPy library, so we create matrices and arrays using NumPy, and then we perform the for loops on those NumPy arrays. But otherwise, we're really not using any packages at all. We just hard coding everything from scratch. And that means that you are in control over everything. Yeah, you're just using the most elementary way of coding and running these simulations possible. So you know exactly what's going on. You're not relying on any packages written by a third party that you don't really understand. So that's what I consider to be one of the main advantages of this approach. You simulate really complex models with this, yeah, it can take a long time for those models to run because you're iterating, and that's computationally intensive. So you run a really large model. Yeah, the approach that we're using is not necessarily the most efficient one, but it's also not really the main purpose of the website. The purpose of the website is to get people into working with simple models, better understanding models. So in a way, that's the trade-off. Either you go for really understanding what you're doing, or you go for building something super complex, but then not necessarily understanding exactly what you're doing. And so we're going for the first option, if you like. We work with relatively simple models, but the advantage is it's completely transparent. We know, everything is sort of transparent. We know exactly what we're doing. So that's what I consider the advantage of this approach. And I've worked with the same approach to simulating models in my own research with also more complex models. And yeah, sometimes then it can take some time for a model to run, but then there's things you can do. You can parallelize your for loop, for example. So through parallelization, you can achieve computational gain. So there's also tools you can use to speed up the computation when you solve models through iteration. Okay, but so let's get back into it. So exercise number 2, very simple. Yeah, I just wanted you to explore a little bit ways of visualizing the results. And one way of doing that for a simple static model like this is a bar chart where you just compare the two solutions. And for those of you who know R, you might be familiar with the bar bar plot function. So that's the built-in base R function to create a bar plot. But I also gave you this tip to just ask ChatGPT, because when it comes to plotting, I highly recommend just asking ChatGPT, because it's very fast and efficient at giving you concise answer to what you're looking for. And I personally don't really see any intellectual benefits anymore in like reading an R manual about how to create a nice looking plot, because this is not really something that I think is scientists would spend their time on. So luckily with ChatGPT, you can get a lot of useful advice on how to create a nice plot. And this is certainly a tool that I would advise using. I mean, just always make sure that in the end, what you get out of ChatGPT is what you're looking for and is correct. But yeah, when it comes to plotting, I think it's super useful. Yeah, so like I say, I would just use the bar plots, the built-in bar plot function here. Let me just check that I'm sharing the right slides. Yeah, okay. And if you do that, you can set some labels here for the y-axis, and you can name the scenarios if you like, and then it will look something like this. Yeah, so here's your rate of capacity utilization for the baseline. I think we found a value of 0.83, something like that. And then for the rise of the profit share scenario, that falls to, what was it, 0.75 or something like that. Yeah? So that's just a way of visualizing that result. And you see that comparison right away. You see that here, there's a fall in the rate of capacity utilization as the profit share increases in the second scenario. Okay. Now I want to talk a bit more about dynamic models in this second part of the lecture. The main disadvantage of static models is that they don't capture the adjustment process from one equilibrium to another, because they don't track how variables change over time. They just give you one equilibrium solution and then a different equilibrium solution, and you can compare equilibria, but you don't know how you get from one equilibrium to another. And they also don't really allow for unstable processes, in the sense that a static model that has an equilibrium that is unstable typically doesn't give you any economically meaningful interpretation of that unstable equilibrium. We saw this briefly when I addressed the issue of instability. We saw that for this Keynesian goods market model, if you set the marginal propensity to consume to larger than 1, the equilibrium becomes unstable, and you get negative values for output, which are economically not meaningful. And when you simulate the model and you start from initial condition of equilibrium, then you get, basically infinitely large values for output. So this doesn't really make any sense. But this doesn't mean that instability cannot be an economically meaningful concept, but it's just something that is not really possible to cover in a meaningful way in a static model. So these are some of the main disadvantages of static models, and that brings me to dynamic models, which allow us to theorize how economic processes happen through time. And this, of course, has lots of applications in economics. So in macroeconomics, we have dynamic structural macroeconomic models, so simple macroeconomic models, which I will focus on in this session. And most of the models on the website are of this kind. Many of you will have also heard of stock-flow consistent models, which are also dynamic models. Agent-based models are dynamic models, and the DSTE models as well are dynamic, as the name says. In microeconomics, we also encounter dynamic models, for example, in evolutionary game theory or behavioral economics and finance. So there's lots of applications of dynamic modeling. And on the empirical side, you work with time series econometrics, where you're essentially dealing with dynamic models as well, because most time series models, such as vector autoregressions, are written as a system of difference equations. So you have that link there to work with macroeconomic time series as well. So how do we go about dynamic modeling? In contrast to static models, the variables in a dynamic model are indexed by time, and we need to make a decision about the time steps that we want to consider. So there's basically two options. So either you think of changes in time as discrete steps, time moving from one discrete unit to the next. And the notation that we use for that is typically the delta. The Greek delta is the change in the variable y from period t to period t plus 1. The other option is to think of time as progressing in infinitesimally small steps. So that's continuous time, where we would look at the change of a variable y over time as the derivative of that variable with respect to time. These are two different ways of modeling time, and you can find both in the literature. In this session, and also with most of the models on the website, with the exception of the Straussian supermultiplier model, all of the models on the website are in discrete time. So I will focus on that. But the good news is that analyzing and simulating continuous time models is very similar. The differences are not huge. And if you're interested in continuous time simulation, then take a look at the Straussian supermultiplier model from the website, because it's in continuous time. So the equations of dynamic models specify how variables impact each other over time. So this can take place either in the same period. So in this example here, if the variable x impacts the variable y in the same period, then the equation will be of this form. But often in dynamic models, we have lagged relationships. So a variable x might impact a variable y only with a lag. And this is then really when our time actually becomes interesting. And a special role is played by the so-called state variables of a dynamic model. So the state variables are those variables that are a function of their own previous value. So if the variable yt happens to be a function of yt minus 1, so its own lagged value, then the variable y is considered a state variable of the model. And the state variables of the model are really what governs the dynamics of the entire model. They will also then feed back into the dynamics of the non-state variables. In that sense, the focus, if you want to analyze dynamic models mathematically, you will really focus on the state variables of those models. Like I said, in this session, because we don't have the time today, we won't go into the mathematical analysis of dynamic models, but I just want to say a few words about it. In a dynamic model, in discrete time, you effectively have a system of difference equations. So you have multiple state variables that interact with each other over time. And the interaction between these state variables is then what generates interesting dynamics. I'm just giving here plots of Hopf bifurcation. I don't want to go into that now, but just as a bit of a teaser, that there's some really cool, interesting dynamic properties that some even simple dynamic models can generate. But to understand these dynamic properties, we need to analyze these models. And one way is, of course, to just simulate the model. So that's what we're going to focus on. But the other route is to analyze these dynamic models mathematically using tools from calculus and linear algebra. And if you're interested in that, I think I mentioned this already. There's a chapter, this is chapter 9 of the macro simulation website, which goes a little bit into the mathematical analysis of dynamic models. So I would refer you to that if you're interested in understanding the underlying mathematics a little bit better. But yeah, for this session, I want to focus on just on simulating dynamic models, and I want to keep it simple as before. So I just want to look at a dynamic version of this post-Keynesian growth model that we just looked at before. And the only change that I'm making here to this model is happening here in the investment function. You see that the endogenous variables of the model are now indexed by time. So we have the time subscript here. And in the investment function, I'm using the lag of the rate of capacity utilization instead of the contemporaneous value as we had in the static model. And in this way, this post-Keynesian growth model becomes a dynamic model because we now have this lagged relationship between investment and rate of capacity utilization. So let me show you how to simulate such a dynamic model. The good news is that the underlying logic and the code for simulating dynamic models is not fundamentally different from what you've seen so far. The main new feature is that we want to keep track of the behavior of the variables over time. And we can then allow shocks to happen at a certain point in time, and we can then check how that affects the dynamic adjustment of the variables to a new equilibrium. So this is the code that simulates this dynamic version of that post-Keynesian growth model. And let me focus on the differences with respect to the previous version of the code. So the first main difference is that we need to decide for how many periods we want to simulate that model. So the first thing we're doing here is we set the number of periods. In this example, I'm just setting the number of periods to 100. Yeah, but you can simulate for as long as you like. Then we set again the number of parameterizations that we want to consider. That's the same as before. And here I'm also creating a variable that defines the period in which we want an exogenous shift or shock to occur. So I'm saying here, okay, in the scenarios that we want to consider, let the change occur in period 40. Okay. Now, when it comes to creating these data structures that will contain the simulated data, the main change now with respect to the static model is that we want to track the evolution of the endogenous variables over time. And we do that by, instead of creating vectors, we're now creating matrices where the rows of the matrix will represent the different scenarios, the different parameterizations that we want to consider. And the columns of the matrices will represent the time periods, the data points for each point in time. Yeah? So here we're creating a matrix that in the first instance will just be filled with ones. And this matrix will have S rows and T columns. And we create such matrices for all the endogenous variables of the model. So for the rate of capacity utilization, the growth rate, the saving rate, the consumption rate, and the profit rate. Then we set the fixed parameter values. So that's the same as before. And now we also construct a matrix for the exogenous variables that we want to shift to consider the different scenarios. So in our case, we want to look at exogenous changes in the profit share. So we create a matrix for the profit share H, and then we create the two scenarios. And the way we do this here is we first fill this entire matrix for the profit share with 0.3. And then in the second row of that matrix, which represents the second scenario, we let the profit share to change from 0.3 to 0.4 from the period that we defined earlier to be the period in which the shock will occur until the end of the simulation. So this expression here means you're accessing the columns that run from SC to T. So in our case, this is the columns 40 until column 100. And for these columns, we change the value of the profit share to 0.4. Yeah. So this is how we create the scenario. And now we solve this system again through iteration. And this is again where another change comes in. And the change is that now, so before we had, remember we had this nested loops where the loop had two levels. We had an inner loop that was the iterations loop, and then we had an outer loop that looped over the scenarios. Now we have a third loop, which is the loop that goes through time. And this loop that goes through time, that sits between the scenarios loop, that the outer loop that goes through the scenarios, and this inner loop that just iterates the model many times, the model equations many times. So between those two loops, we have this new loop now where we use the index letter T to represent time. And this T index will then run from the second period onwards to the third, fourth, and so on until the last period. And now if you look at the equations inside the inner loop, you can see that the squared brackets that we use to access particular elements of a vector or matrix, these squared brackets, they now have two components. The first one refers to the rows of that matrix, and the rows of the matrix represent the scenarios. And because we are using for the scenarios loop, we're using the index letter I. That's why to access the relevant rows of the matrix, we also use the index letter I here. And then we have a comma, and after the comma, we have the letter T. So the point after the comma represents the columns of the matrix, and the columns of the matrix we wanted to represent time. And so this is why we're using the time index here, because we will, in this way, we will access the relevant columns of the matrix and store the values that represented the change of the variable over time in the correct column of the matrix. Yeah. So you can see that all the endogenous variables here, they are now indexed by this I, T notation. Yeah. And in this way, we fill in the right values for the correct scenario at the correct time period. Yeah. But otherwise, we're just writing down the same equations as before. And then in the end, we first close the inner loop, the iterations loop, then we close the time loop, and then we close the scenario loop. And then we can display the solutions by accessing the last element, the last column of whatever variable you're interested in, which represents the solution for the last period, where you can assume that you've reached equilibrium if the model is stable. Yeah, so let me just go to the, if we run this, you can see we get the same solution for the rate of capacity utilization as before. Yeah, so if we print the solution for the final period of the simulation, we again get 0.83 for the rate of capacity utilization for the case where the profit share was set to 0.3. And for the second scenario, where the profit share went up to 40%, rate of capacity utilization fell to 75%. It's the same result here. The fact that we now have a lag in the rate of capacity utilization here in our investment function hasn't changed the equilibrium solutions of the model. The equilibrium solutions of the model are still the same. And the dynamic simulation will also still give you the same equilibrium solution because, yeah, like I said, I'm introducing this lag relationship doesn't change the equilibrium solution. But what it does change is the adjustment towards that equilibrium. And that you can see best by plotting the data. So that's what I'm doing here in the next chunk of code. So I'm setting the start and end periods for the plot that I want to generate. Here I just say, okay, let's plot from the first to the last period. And then I'm using the plot function to plot the rate of capacity utilization. And I'm plotting it both for the baseline and then also for this second scenario where the profit share goes up 2.4 in period 40 or whatever it was. And then there's some more stuff here, adding a legend. Like I said, this is now, this is the little bit tedious coding stuff to create a nice looking plot. But like I said, with ChatGPT, this has become a lot easier to do. If you run this, the figure will look like this. Yeah. So what is going on here? So the solid line gives us the baseline solution for the rate of capacity utilization. So in the simulation where we keep the profit share fixed at 0.3, and then the dotted line or dashed line, that's the simulation for the second scenario where the rate of where the profit share increases from period 40 onwards and then stays at this higher value from period 40 onwards. And you can see that we have some adjustment dynamics happening in place right at the start of the simulation. And this is because we're not initializing the variables of the model in equilibrium. Yeah. Here, remember, when we constructed the data matrix, we set the values of rate of capacity utilization, growth, and so on equal to 1. Yeah? So we initialized all of these variables at 1, which is, of course, not the equilibrium solution. So we're initializing these variables outside of equilibrium, which means that the adjustment dynamics that we're seeing here in the beginning, this is just because we're starting from this initialization of equilibrium. And the first thing we observe here is the adjustment towards that equilibrium. So that's what's happening here in the beginning. Now for the baseline, this adjustment after 15 periods or so, from that initialization, we are on the equilibrium solution, and then we stay there. Yeah, equilibrium solution of 0.85. But then for the second parameterization in period 40, this additional shock occurs where the profit share rises. And this then creates a new adjustment dynamics, which play out relatively quickly and bring us then to this new equilibrium of 0.75 for this second parameterization. Yeah, so here, the fact that we have a dynamic model now allows us to consider these adjustment dynamics from one equilibrium to the next through the numerical simulation. So that's really the main change here from the static model to the dynamic model. Okay, any questions up to this point? No. Okay, great. So then let's simulate a dynamic model in the lab. And the model I want you to simulate is not the post-Galetsky model, but it's a different model. I want you to simulate a multiplier accelerator model, which is a dynamic Keynesian business cycle model that was developed by Paul Samuelson in 1939, so a long time ago. And this model captures the interaction between the Keynesian multiplier effect on consumption and the accelerator effect on investment. And more or less what's going on in the model is that you have an increase in investment, which boosts consumption via the multiplier effect. But then this increase in consumption then has a negative feedback effects on investment. And this interaction can give rise to cycles under certain conditions. The model has these three equations. So we have the first equation is the familiar Keynesian output equation, where we have aggregate output on the left-hand side, and on the right-hand side, we have aggregate demand. And in this model, aggregate demand consists of consumption, investment, and government spending. Then we have this accelerator equation for investment. So investment is increasing in the change in consumption from period t-1 to t. And then finally, for consumption, we have a simple Keynesian consumption function. There's no autonomous consumption here, just the market to consume all of past periods or previous periods' income. Yeah, so that's these are the equations of the multiply accelerator model. Now, I mean, in a way, you could simulate just the model the way it is. If you want to analyze the model mathematically, which we're not going to do in this session because we don't have time, but on the website, I'm doing this. And that's why I'm introducing a slightly different representation of the model, which is useful later on if you want to analyze the model mathematically. So what I'm doing is I'm shifting all the time subscripts in the output equation back by one period. And so I get an equation for yt-1. And then I use this equation for yt-1 in the consumption function, yeah, because here we have yt-1 in the consumption function. I plug that into the consumption function. And then I plug that expression for consumption here into the investment function. And then I get a system that looks like this. The main advantage of this representation of the model is that now you have the model written as a system of difference equations in the two state variables of this model, which are consumption and investment. So you can see consumption is now a function of past consumption and past investment. And investment is a function of past consumption and past investment. And otherwise, there's only exogenous parameters or this exogenous government spending in these equations. Yeah, so this is now a neatly organized system of first-order difference equations. And this is useful for mathematical analysis if you want to analyze it mathematically. Okay, but what I want you to do now is just to simulate the model, setting the consumption function, setting the marginal difference to consume to 0.8 and the accelerator coefficient in the investment function equal to 0.3. And then I want you to consider a scenario where government spending rises from 5 to 6. And I want you to plot the results for output. So you can use the code here on the next slide. And you can see there's some parts that are missing, yeah, where I want you to fill in the gaps. So that would be here and here where you need to implement the government spending shock. And then the rest should work. And well, I think I already gave you the code also to plot output once you made those changes. So output should then appear as well. Okay, so let's take 5 minutes or so. And I give you a chance to try to do it on your own, yeah? Okay, just to take a look at this together. So let me switch to my R screen. Okay, so okay, we need to set the parameter value. So we set marginal balance consume. What did I say for the marginal balance consume? So 0.8 again, and beta we want to set at 0.3. Then for this government spending shock, okay, we said we want. So here we're setting government spending at equal to 5 across the board. And then we said that in the second scenario, we want government spending to rise from this shock period onward. So that's S, lowercase s, until the last period. And we want government spending to go up to 6, I believe. Yeah, okay. So that should be it. So sorry, that's this line here. Yeah, that's our government spending shock. And then otherwise, yeah, the equations are already there. So these are the two equations of the model. We have the iterations loop, we have the time loop, and we have the scenarios loop. And then what we're doing here is we're calculating the solution for output outside of the loop. Because the only thing we need to find the solution for output is the values for consumption, government spending, and investment, which we have at this point. Yeah, so we can calculate output ex post, if you like, outside of the loop here. So we run that. So we can just run this now. Yeah, and then this should give you the simulation here for output under the government spending shock. So we have our baseline, as in the dynamic version of the post-collect skill model I showed you before. Because we initialize the variables outside of equilibrium, we get some adjustment towards the equilibrium right from the start in the baseline. And then in the second scenario, where we additionally get this change in government spending from period 15 onwards, we then get pushed away from that previous equilibrium towards the new equilibrium. And we can see we have some adjustment dynamics taking place to that new equilibrium here along the way. And because this is a Keynesian model, for a higher level of government spending, we get a higher level of output. Someone.
Falei, rapaz, eu fui lá na sala da minha mãe, que ela me chamou. Cheguei lá, não tinha ninguém. Eu falei, quer ver que elas estão lá na minha sala comendo?
Alô, quem está com o microfone aberto, por favor, fecha.
Ninguém apareceu hoje aqui, não.
Alguém está com o microfone aberto, está atrapalhando o curso.
Vou só cuidar aqui.
Wesley, acho que é o seu microfone.
Eu mexi aí para fazer um chá. Eu mexi para fazer um chá e vou consertar, calma. Na verdade, consertar
Wesley,
não,
por
né?
favor, fecha o seu microfone.
Porque o Diego tinha deixado bonitinho, vou lá disso para ligar a máquina. Aí você desembolou para quê?
Não estava tão assim fácil de colocar, não.
Não, porque eu já tinha olhado.
Já?
Professor, eu acredito que quem é o host da
Daniel,
reunião...
Daniel. Sorry, Karsten, but I do not have the power to... I'm not the host. The host
Yeah,
is
the host needs to mute everyone.
Okay, I think that now it's okay.
Okay. Okay, good. Yeah, so these are that's basically what we would expect from this Keynesian model. Yeah, so with a higher government spending, we jump towards this new equilibrium where we reach a higher level of equilibrium output. Let me change back to the slide. Yeah, so that was the solution. Okay, there's one more thing I want you to do now, which is to change the parameterization so I want you to set this value of 2 for beta. We want a much stronger accelerator effect and a slightly lower marginal propensity to consume of 0.4. And then you can just keep government spending fixed at 5. We are not interested in the change in government spending at this point. And then simulate the model for this parameterization and plot consumption and see what happens. Okay, so that's the next thing I would like to do now. So for those of you who successfully simulate the model for this new parameterization, if you like, you can write in the chat, what's the main difference? What's the main new feature that you observe for this this parameterization? So I should say, this is the plot that you should get for exercise 3. Because we had a question about exercise 3. This is how the plot should look like for the previous exercise. Okay, so Joao said for this new parameterization defined cycles. So that's correct. That's the main new feature. If you, so maybe let's just do it together again. So let me copy and paste the code. So we set marginal propensity consumed 0.4, beta to, what was it, 2? Beta equal to 2, and government spending just keep at fixed at 5. And then we plot consumption. So here you need to choose the C. And that's it. These are the only changes you need to make. And then you should get something like this. So you can see that we get these cyclical adjustments towards the equilibrium. Yeah, so just going back to the sorry, here you can see it. Yeah, so if you set beta equal to 2, multiply to 2.4, we just keep government spending fixed at 5. Now we only look at the baseline scenario, and then you run the whole thing. This is the value for consumption, that the solution for consumption that you would get. So you can see that for a different parameterization, this multiply accelerator model can give you cycles. And that was actually also the intention that Samuelson had when he designed that model. He wanted to create a simple Keynesian business cycle model. And you can see that apparently as we increase the beta coefficient, this accelerator coefficient, to a much higher value, while also lowering the marginal propensity to consume, we get a different dynamic properties for this model. Yeah, for the previous parameterization, we didn't have these cycles. Now we get this cyclical adjustment. And of course, that means that let me just go back to the slides. That means that this model under certain parameter configuration can give you cycles, but it will not necessarily always give you cycles. And this is again, an illustration of this feature that we have talked about before. With a numerical simulation, you look at a parameterization at a time, yeah? And you might study the model under certain parameterization and conclude the model doesn't give you cycles. But for a different parameterization, the model might give you cycles. In the case of the Samuelson model, because it's a very simple model, we can actually work out an exact mathematical condition under which the model gives you cycles. And the chapter 9 on the website discusses that in more detail. Yeah, that chapter on the mathematical analysis of dynamic models derives in detail the condition under which the model gives cycles. So that's useful if you want to understand a little bit better what's driving these cycles here that we find in the simulations from a mathematical point of view. Yeah, Carlos, I will share at the end of the session the version of the slide for the solution. Yeah, so I'll share those at the end. Okay, any other questions up to this point? Okay, so then the last thing I wanted to show you today is a directed graph. So directed graphs provide a neat graphical representation of the causal structure of a model. A directed graph consists of a set of nodes that represent the variables of a model, and then a set of arrows, or sometimes called edges, that connect the variables of the model. And if you have an edge that is directed from a node X to a node Y, that indicates the causal impact of the variable X on Y. Yeah, so very simple idea. And these directed graphs are now used quite widely also in the empirical literature, especially in causal inference literature. In computer science, they're quite popular. So you might encounter these in other contexts as well, but we can also use them to represent the causal structure in economic models. And so that's why I think they are a useful tool. And one way to obtain a rigorous representation of a directed graph that corresponds to a particular model is to take the so-called Jacobian matrix of a model. Yeah, so we can collect all the endogenous variables in a vector y, and then we can write this economic model as a system of equations. So f here, f of y is then the system of equations that make up that model. And then the Jacobian matrix is defined as the matrix that contains all the partial derivatives of those equations with respect to each of the variables of the model. Yeah, that's the way the Jacobian matrix is defined. If you have a linear system, then the Jacobian matrix coincides with the so-called coefficient matrix. Yeah, the matrix that contains all the coefficients that are multiplied onto the endogenous variables. The Jacobian matrix is just a generalization of the idea of a coefficient matrix that is also applicable to nonlinear systems, where you just put all the partial derivatives with respect to all of the variables in a matrix. Yeah, that's all that is there to a Jacobian matrix. And you can also include the exogenous variables of a model in the Jacobian. But these will have rows that will only contain zeros because they don't change. Yeah, so the rows in the Jacobian matrix that represent the exogenous variables of the model, they will only contain zeros because, well, yeah, they don't change. So the derivative of any other variable will be zero for a exogenous variable. But these rows with the zeros, they are relevant when it comes to constructing the directed graph. So you see that in a second as I show you an example. So as soon as we constructed this Jacobian matrix, the next thing we need to do to construct the directed graph is to construct what I call here an auxiliary Jacobian matrix. Let's call that matrix M. And this auxiliary Jacobian matrix, in this matrix, we set all the non-zero elements of the Jacobian equal to 1. And all the zero elements, they just remain at 0. Yeah, so this matrix M is just a matrix that only contains ones and zeros. And the ones in the matrix represent elements of the Jacobian matrix that are different from 0. And the zero elements, they just represent zero elements in the Jacobian matrix. And then finally, what you do is you take the transpose of this so-called auxiliary Jacobian matrix, which then gives you a matrix that is called adjacency matrix. Yeah. So adjacency matrix A is defined as the transpose of this auxiliary matrix. And this adjacency matrix is a binary matrix whose elements indicate whether there is a directed edge from a node yj to a node yi. It basically contains information about whether there is a causal effect of a variable from your model to another variable in your model. If there is a causal effect, then that matrix contains, the relevant element in the matrix contains a 1. If there's no causal effect, that matrix contains a value of 0. Yeah, so that's the information you get from this adjacency matrix. And for those of you who have encountered some network analysis before, the adjacency matrix is really one of the key components in network analysis. In network analysis, it's very common to draw these directed graphs. For example, if you have an input-output network, you can represent that with a directed graph. And the adjacency matrix tells you whether there is a linkage between two different sectors. So you might have encountered this concept of the adjacency matrix in other contexts as well, because it's a really foundational concept in network analysis. And the nice thing is that now we have created this adjacency matrix from the Jacobian matrix of our model, we can then draw this directed graph based on that adjacency matrix. And then we, in a way, we have a rigorous link that takes the model and transforms it into an adjacency matrix, and then we can generate this graphical representation of the model. So here I'm doing this for this post-Keynesian growth model that we studied before as an example. And what I'm doing here is I'm creating this matrix M, this auxiliary matrix M. For some reason it kicked me back to the beginning. So I'm setting up this matrix manually here by creating a matrix in R. And here I'm just doing this manually, yeah, because that's ultimately the easiest way of doing it. You just look at the equations of your model, and you decide, is there a causal relationship or not? So here, the first endogenous variable in the model is the profit rate R. So the first row here in this matrix represents the profit rate. And then for the profit rate, we ask the question, what are the other variables that determine the profit rate? So the first column is the in a way the effect of the profit rate on itself, so that we keep that at 0 because there's no feedback loop from the profit rate to itself. So that's why we put a 0 here. Then the next column is the saving rate. There's no direct effect of saving on the profit rate, so that's why we have a 0. There's no direct effect of the growth rate, which is the third column, on the profit rate, which is why we have a 0. But then we do have the rate of capacity utilization determining the profit rate. So that's why we set this element here equal to 1. And then the profit share, H, the last element in our matrix, has a direct effect on the profit rate using the profit rate equation. And that's why we set this equal to 1 as well. And we do the same thing for all endogenous variables of the model. And then the last row represents the main exogenous variable of the model, which is the profit share. So here, like I said before, because the profit share is exogenous, nothing impacts the profit share. All of the rows in this row representing the profit share, we set equal to 0. Then we take the transpose of this auxiliary matrix, and we assign the column names to the matrix to remind ourselves, okay, the first column represents profit rate, second column represents saving, and so on. And then we create this directed graph. Well, this is where we rely on a library. We don't do this from scratch, but we have pretty much done everything from scratch except drawing on this iGraph library that then creates that directed graph from that adjacency matrix. And so that's what we're doing here in the last line. And this is how the directed graph for this post-Keynesian growth model looks like. So we have our 5 endogenous variables: profit rate, rate of capacity utilization, saving rate, and growth rate. And then here the profit share represents the main exogenous variable of the model. And then we have these arrows that now represent the causal relationships from that model. And maybe when you look at this for the first time, you just see like, okay, there's a bunch of nodes and then some arrows, and why is this useful? But if you take a closer look, there's actually quite a lot of useful information in this direct graph. So to illustrate this, we can identify 3 types of nodes. The first node in a directed graph is the first type of node is one where from which arrows only point away. And these nodes represent the exogenous variables of the model. In our case, this is H. If you go back to the directed graph, you look at the node A, you can see that from this node A, the arrows only point away. There's no arrow pointing towards H. And this represents the fact that in this model, the profit share is assumed to be exogenous. Then secondly, we have nodes towards which arrows point, but from which arrows also point away. And these nodes represent the endogenous variables of the model, in the sense that they are being determined by other variables, but they also have feedback effects on other variables. And if you look at this post-Koletskin model, the rate of capacity utilization, the saving rate, and the growth rate, these are examples of endogenous variables. So if you take the rate of capacity utilization U here, you can see the rate of capacity utilization is determined by the saving rate and by the growth rate. But at the same time, the rate of capacity utilization also has an effect on the growth rate and on the saving rate. So we have bidirectional arrows here between the saving rate and the rate of capacity utilization, and also the rate of capacity utilization and the growth rate. And we have an arrow from the rate of capacity utilization to the profit rate. So in that sense, the rate of capacity utilization is both being determined by other variables, but it also impacts other variables in the model. And then the last type of node that we have are nodes two arrows. So we have nodes that only have inward arrows. I think I need to rewrite this sentence because it's a bit weirdly phrased here. But basically, we have these endogenous variables that are completely determined by other variables, but have no effect on other variables. So this is the case of the profit rate in this model. You can see that there's two arrows pointing towards the profit rate, but there's no arrow from the profit rate to any of the other variables in the model. And this variable we sometimes call a residual. Yeah, so the profit rate in this model is a residual variable. It is not. It is completely determined by all the other variables in the model, but has no own effect on any of the other variables in the model. Yeah, and so this is something we can see by looking at the arrows, and it tells us a little bit about the causal role of different variables in our model, and this can help us also think through the causal structure of the model, and perhaps also to what extent we find these assumptions plausible or not when confronting them with the real world. Yeah, so for a simple model like this, you might not gain like very surprising insights from creating a directed graph, but as soon as you work with models that have more variables, like 6, 7, 8, 10 variables, and you create a directed graph, I think it can really help you to think through the causal structure of the model. So I think that's one of the main advantages, which is why I think they are useful. So the very last lab session that I prepared was to create a directed graph for this multiply accelerator model. So we only have 5 minutes left. So we can give it a go, but if you want to leave for something else, that's also fine. Yeah. So I'm going to give you 2 minutes to take a look, and then I give you the solution, and then we finish. So on this next slide, I already created the basic structure to produce a directed graph for this Samuelson model. The only thing that's missing here are the elements in this adjacency matrix. Yeah, so you have to fill this matrix with zeros or ones. And the way to do this is you need to go back to the equations of the model. Yeah, so what is it? Equation, sorry. Slide 33 contains the equations of the model. And we then say, okay, let's order the equations such that our first row is going to be the row for output, the second row is going to be the row for consumption, and the third row is going to be the one for investment, and the fourth row for exogenous government spending. And then you look at the equation for output, and you ask the question, is output determined by itself? Well, no, in this case not. So you can set a 0 here in the first element. But we know, for example, that output is determined by consumption. So we set a 1 here in the second column that represents consumption. And yeah, then you do the same thing for all the equations of the model. But since we're out of time, I'll just jump to the solution. Yeah. So if you go through this one by one, the adjacency matrix will look like this. Yeah. So we typically have zeros on the main diagonal because we don't really have variables kind of impacting themselves. And then for output, we have an effect of consumption on output and of investment on output, and also of government spending on output. So that's why we have the 1, 1, 1 here. And then the same thing for you go through these other equations, and this is how you would fill the matrix. And then yeah, if you plot it, it will look like this. Yeah. So this is even simpler because we only have these 3 endogenous variables: output, investment, and consumption. And you can see the key exogenous variable is government spending. Government spending feeds into output, and then we have this circular structure that links output, consumption, and investment. Okay, before I forget this, let me upload the solutions as well to the chat. So these are the solutions. If you want to take a look at these exercises at home and check that the solutions are correct, then feel free to use these slides. And I'm just going to finish the session. So what are the main messages, main takeaways that I wanted to convey today? So yeah, I think economic models are useful because they allow us to analyze causal mechanisms. And this is useful for understanding major macroeconomic events and for devising appropriate policies. And to be able to do this properly, we need to have a deep understanding of economic modeling so that we can really use economic modeling to understand these causal relationships. And this can be achieved best by combining both mathematical and numerical analysis. In an ideal world, they kind of both supplement each other. And yeah, I hope that the website provides some resources to help you do both sort of improve your mathematical understanding and your numerical understanding of economic models so that you can take advantage of them and use them for policy analysis and whatever you're interested in. Okay, that's what I wanted to cover. I'm happy to answer any last questions if there's any questions you have.
Karsten, can I ask a quick question?
Of course.
Python or R, like, is there one that just basically? So I'm doing some work with the central bank and how it interacts to produce the Goodwin pattern. I'm currently using MATLAB and I'm finding it very, very difficult. Although I've worked through the model, I'd like something a little bit easier. Do you prefer to work in R or Python, or what are the benefits to each for doing these kind of macro models?
Yeah, thanks, Chris. I mean, first of all, the difference, I guess I probably don't have to mention, but I'll do for the record anyway. The main difference between MATLAB versus R and Python is, of course, that R and Python are open source and free. So I think that's really the main advantage, and I think there's long-term gains for learning any of these open source programming languages, because you don't really rely on these having a license for any of these private inexpensive software. When it comes to the difference between R and Python, I would say that our Python is a bit more general purpose than R. R has been designed specifically for working with the vectors and matrices and doing, working with numbers, numerical analysis, statistical analysis. Whereas Python is more general purpose. You can, program computer games in Python or whatever. You can do more things in Python. But for the purpose of working with data, both numerical simulated data or empirical data, I personally don't really see why you would, what kind of functionality there is in Python that you don't have in R. I mean, besides any particular packages that some people might have written that's only available in Python but not in R. But I think it's always the case that maybe there's one method you want to use. Someone has written a package that only exists in Python or R. You never really know. That depends on the particular package. But when it comes to the elementary stuff, I don't really see a big advantage of Python over R. I think you can do everything you want to do in R, and certain advantage of R, I think, is sometimes that sort of, you're just working with very elementary matrices and vectors, which are kind of really the basic structures in R. Whereas in Python, so for example, if you want to work with matrices and vectors, you use a library, the NumPy library, and then you can, from that library, you can use the data structures that come with that library to work with them. And sometimes I personally find them sometimes a little bit cumbersome, that I first have to kind of rely on this library. And when it comes to running these simulations with an iterations loop in Python using NumPy arrays, it tends to be a bit slower than R. And I think this is because you're not really using a kind of an elementary structure in Python. You're using something that comes from this NumPy library, and that slows things down a little bit. And this is why for the approach that we're using on the website, Python tends to be a bit slower than R. So that's why I personally have a slight preference for R.
Okay, but that's what I was thinking.
Yeah, but I don't know. I mean, the question is, if you want to do other things later in your life in programming, maybe it can make sense to do Python now, because then you are used to it, and then you can also do other things beyond working with numbers. Well, I don't know how realistic that scenario is.
Yeah, I think just for me, I'm doing basically theoretical macro models, kind of what you're working on here, and it just seems like just R is probably the better fit for that. And then with empirical stuff, I just use Stata. I don't even use R for the empirical stuff. Yeah. Even though R can handle that, obviously.
Yeah, I think it's really, I don't think the differences are huge. I think once you are used to either R or Python, switching to the other one is relatively easy. And you can also now get your codes translated by ChatGPT. I mean, as always, right, you need to, of course, double check that ChatGPT makes errors, but it still can save you a lot of time and give you like a first draft, of a translation of a code, and then you make sure that it works. But yeah, I think it's become a lot easier, I think, now to switch between the two. So I don't think it makes a big difference. Yeah, like I said, personally, I have a slight preference for R, but it's probably just because I've worked a bit longer with R than with Python.
Okay, that makes sense.
Well, if there is no other questions, let us end the course. And before it, I would like to thank to Professor Karsten Kohler to have accepted my invitation to give this mini course on simulation, computer simulation of macroeconomic models. This mini course was a joint initiative of the Structuralist Development Macroeconomics Research Group that is coordinated by me and the Regional Council of Economics at Distrito Federal in Brasília. So, Karsten, thank you very much for your course. I think that it was very useful for people to understand how to use the computer simulation in macroeconomic models. And I think there is a thing that we in our University of Brasília must take seriously, and to use this kind of tools in our macroeconomic courses in order to facilitate the understanding of the basic macroeconomic models teach at undergraduate, for instance, the Keynesian, simple Keynesian model, the SLM, the aggregate demand, aggregate supply model, the three-equation model, which is the new Keynesian version of TSGE. And so I would say that it's marvelous to have you with us. Professor Karsten is actually in a sabbatical year at the Federal University of Rio de Janeiro, so he's speaking from Rio de Janeiro. And well, many thanks, Karsten.
Thanks for the invitation. I enjoyed the session, and yeah, thanks everyone for joining. If you have any questions, encounter any problems with any of the material on the website, always feel free to just send me an email. I'm happy to answer questions.
Okay, people, so let us, it's officially declared closed, the course. Many thanks and see you later. Bye-bye.
Bye-bye.